Next we have Corollary 1259, which states that if x comma d is a metric space and these ki's form a sequence of non-empty compact subsets of x such that it's a nested sequence, k1 contains k2, k2 contains k3 and it goes like that, then the intersection of all the k's is also non-empty. And this claim will be proved when we solve exercise 12.5.6. And finally we have theorem 12.5.10. This is the last result of this section. Again, let x comma d be a metric space. There are three parts. This is part A. Part A states that if y is a compact subset of x and z is some subset of y, then z is compact if and only if z is closed. You can also say it like this. In a compact space, a subset is compact if and only if it's closed. Or in other words, in a compact space, closedness and compactness of a subset are equivalent. Next, part B states that if y1, y2 up to yn are compact subsets of x, there are finitely many compact subsets, then their union is also compact. And then we have part C, which states that every finite subset of x, including the empty set, is compact. And we will prove this result when we solve exercise 12.5.7. So here the section ends. But let's also solve two exercises. So the first exercise asks us to show that definitions 9.1.22 and 12.5.3 match when talking about subsets of R in the standard metric. This is the definition of boundedness of a subset of R, I mean this one that we saw back then, and this one is the definition of a subset being bounded in a metric space, a general metric space. These two definitions are supposed to match when we are in this metric space, the metric space of real numbers in the usual metric. Let x be a subset of R, and let's start by assuming that x is bounded according to the old definition. That means x will be contained in a closed interval like this, minus m comma m for some positive real number m. Then x is obviously contained in this open interval also, minus m minus 1 comma m plus 1, because this is contained in this. But this open interval, however, is the open ball centered at 0 having radius m plus 1. And this is an open ball in R in the usual metric, standard metric. And that is why by definition 12.5.3 also x is bounded. Conversely, let x be bounded according to definition 12.5.3. Now we have to prove that then x is also bounded according to definition 9.1.22. Then x will be contained in some ball B with center x and radius r for some real numbers x and r, where r of course is positive. Now choose a positive integer capital N which is greater than the maximum of x plus r and r minus x. We can do this, that is such an N will exist because of the Archimedean property that the real numbers have. By that property in particular, there is no largest positive integer, and in fact even more than that, the positive integers form an unbounded subset of the set of real numbers. No matter how large this maximum is, whatever it is, there is a larger positive integer. Then minus n is less than x minus r is less than x plus r, and x plus r is less than n. It's pretty easy to understand how this last inequality comes. Because n is greater than the maximum of these two, obviously n is greater than x plus r in particular. What about this middle inequality? This middle inequality is true if and only if minus r is less than r, which is true if and only if 2r is greater than 0. But that is true because r itself is positive here. And what about this first inequality? Note that n is in particular greater than r minus x. So minus n is less than x minus r. So that's how these inequalities come. Hence we have these containments. X we already know is contained in the ball Bx comma R, and in the space of real numbers that ball is nothing but this open interval x minus r comma x plus r. But note that because of these inequalities, this open interval itself is contained in the closed interval minus n comma n, because the boundary points are within the region between minus n and n. That's why. But then what does this mean? X is contained in a closed interval like this. It just means that by definition 9122 also X is bounded. So this is where the solution ends. Next we have exercise 2, which tells us to prove proposition 1255. This was the statement of proposition 1255. Let X comma D be a compact metric space, then it is both complete as well as bounded. Now we have to prove this. To prove that X is complete, we need to show that every Cauchy sequence in X is convergent. So let Xn be a Cauchy sequence in X. Now because we are in a compact space, so any sequence has a convergent subsequence by the definition of compactness. This is a Cauchy sequence, fine, but it's after all just a sequence. So this one will also have a convergent subsequence x and j, say, where j varies from 1 to infinity. That means there is some point L in the space x to which this x and j will converge as j approaches infinity. And that is why by lemma 1249, the original sequence xn also converges to that point L. You go back and check the statement of this, it says that if even one subsequence of a Cauchy sequence converges to some point, then the entire Cauchy sequence converges to that point. And that's why x comma d is complete. So it's just that. We have one half of it. Now next we need to prove that x as a subset of itself is bounded. But before I do that though, let me say something about the notation I am using here. Ideally, I should have written d dash limit xn as n tends to infinity, because we are in the metric d. However, I am using this more simple notation with the understanding that the underlying metric is d. Okay, so I am not using that ideal notation. Suppose x is not bounded, so we are going for a contradiction. Then obviously x cannot be the empty set, because the empty set is bounded. So that means there should be something in x. So arbitrarily choose a point small x in x. Now what does it mean for x to be not bounded? It means that x will not be entirely contained in some single ball centered at some point and having some radius. In particular, for each positive integer n, x will not be contained in this ball whose center is that x and whose radius is n. In other words, there will be something in x outside this ball, or in other words, this set difference will be non-empty for each positive integer n. So you now have an infinite collection of non-empty sets. All these x difference b of x comma n as n varies over the set of positive integers. So by the axiom of choice, you can choose one element from each set, and that's how you get a sequence yn, where n varies from 1 to infinity, in such a way that yn has been chosen from this nth set difference, okay, not this ball only. Actually, yn will lie outside this ball, and that is why yn does not belong to this ball for each positive integer n. Now we are still in a compact space x, and this is a sequence, so there will be a convergent subsequence y and j, where say j goes from 1 to infinity, and say that converges to some point set of the space x as j approaches infinity. And because of this convergence, we are now going to get a positive integer j, say capital J, such that the distance between y and j and z, that limit, is at most 1, is less than or equal to 1 for all j greater than or equal to j. This comes from the convergence of this sequence to z and the definition of convergence, the epsilon n definition. In this case, in place of epsilon, we have 1. Now next we have this. Ni is greater than the maximum of 1 plus the distance between z and x. Do not forget what x is, okay? X was that first chosen point x. And nj, n capital J. You will see why we have chosen this strange number here. But right now let's just assume that this is something. Something means what? It's after all a real number. And we are saying that Ni will be greater than this maximum value for some positive integer I. But why? What is the reason? The reason is that since Ynj is a subsequence of Yn, so if you only collect these nj's, the suffix values, then they will form a subsequence of the sequence of positive integers. And such a subsequence is unbounded above. It's strictly increasing also, and that is why it exceeds every real number eventually, no matter how large this number is. Eventually, that means for a large enough I, you will find Ni exceeding this. It's even greater than that. Alright, but then we have something which is actually wrong. Let's see what it is. We have written Ni here, and we are saying that it is less than or equal to the distance between Yni and x. Where is this coming from? This is coming from the construction of the sequence Yn itself. How did we construct it? According to that choice, according to the choices of the Yns, Yn does not belong to the ball bx, n. That means the distance between Yn and x should be greater than or equal to n. That is why the distance between Yni and x should be greater than or equal to Ni. So it's coming from there. But then we have used the triangle inequality to inject this intermediate point z. Intermediate means it's just a way of saying, okay. So this is less than or equal to the distance between Yni and z plus the distance between z and x. However, this is less than or equal to 1. Provided this I is greater than or equal to j. How do we know that I is greater than or equal to j? That comes from here. Because Ni is greater than the max of these two numbers, Ni in particular is greater than Nj also. But because these Nj's, n small j's, form an increasing sequence of positive integers, so for this to happen, I has to be greater than j. That is why I chose this other number like this here. Alright, so that means this actually is less than or equal to 1 for I. Alright, so now we have this. However, our Ni is greater than this also. So this is less than Ni. But this is a problem because we have proved that Ni is strictly less than itself. So obviously it cannot happen, so we have got a contradiction. So now we can conclude, but this is a contradiction, so our supposition must be wrong, i.e. x must be bounded. So this is where the proof ends and obviously the solution also ends.